Level 0. The stars shine, satellites hum in perfect orbit. Your GPS works, your internet flows, space feels silent, clean, empty. But that's the illusion, because the universe doesn't sleep. It seethes, it pulses, and sometimes it throws a tantrum. This is level 0, the calm before plasma. There are no warnings, no rumbling clouds, just an invisible stream, charged particles drifting from the sun, guided by the solar wind. They seem harmless, and they usually are. But even peace in space is loaded with potential energy. At this level, continuous satellite monitoring and early detection systems give us precious time to act if conditions shift. Prevention begins with awareness. Level 1, a tiny blip, a brief dropout. Your car's GPS glitches for a second. You wouldn't think to blame the sun, but that's exactly where it started. Mild solar wind, just enough to brush against Earth's magnetic field. Not enough to panic NASA, but enough to confuse polar flights. Enough to make auroras dance over places they don't belong. We call it a G1 geomagnetic storm. Harmless, most say. Until your plane loses high-frequency comms over the Arctic, until a polar research station can't send data, until your smart grid hesitates for just a moment, it's the first tap on the shoulder. A quiet reminder that our magnetosphere isn't invincible. Power grids start humming, satellites feel it. Solar panels, battery systems, navigation payloads. No explosions, no drama, but systems strain, and strain over time is how things break. Airlines reroute high-latitude flights during geomagnetic spikes to avoid HF radio loss. Staying updated with NOAA space weather alerts is essential for aviation, marine, and satellite operations. Early awareness keeps small storms from becoming big problems. Level 2. The sunspot looks small, just a blemish on the star's surface. But it's twisted, magnetic lines wrapped like coiled snakes, tangled and tense. And when they snap, they don't whisper. They roar. An M-class solar flare is unleashed, a violent surge of ultraviolet and X-ray radiation. It doesn't crawl, it moves at the speed of light. And Earth has no time to duck. The ionosphere takes the hit. Your plane crosses the Arctic skies, where satellite coverage is thin and radio waves matter. Then, silence. No more HF communication. Below, satellites pick up the spike. Some switch to safe mode. Others glitch. Minor misfires, corrupted data packets, phantom restarts. One weather satellite goes blind, logging cloud patterns from the wrong hemisphere. It's not catastrophic. No explosions, no burning circuits. Just quiet, invisible interference. But in orbit, quiet doesn't mean safe. This is where disruption begins, not with a bang, but a blink. Systems reboot, pilots switch to backup channels. Mission control takes a deep breath and resets a few protocols. But it's not nothing, it's a warning. Backup satellite communication systems and predictive modeling help prevent disruptions to aviation and space services during moderate flares. Investing in radiation-hardened satellite design minimizes long-term risk and protects both orbiting assets and those relying on them below. Level 3, this time it's personal. You're in the dark, literally. Your phone still works, barely, but the ATM won't. The train signals are frozen, airport runway lights flicker and vanish. It's not a power outage from rain or a fallen tree. This is something bigger, hotter, faster. A CME, a coronal mass ejection. 1 billion tons of plasma launched from the sun's surface, traveling at nearly 1,000 kilometers per second. And it's aimed straight at Earth. You don't see it, but the planet does. Earth's magnetic shield bends under the blow. It strains, then shudders, and the currents begin. Electric currents, ground-induced and unstoppable, surge through high-voltage lines, designed for stability, not for space weather. Transformers groan, circuits overheat, power stations miles apart flicker in unison. In 1989, a storm like this took down all of Quebec. 6 million people plunged into darkness in under 2 minutes, not because of war, but because of the sun. This isn't just about satellites anymore. It's about the fragility of modern life. The illusion that our grid, our data, our comfort can survive anything. Grounding power systems and installing surge protection in transformers can drastically reduce large-scale blackouts during geomagnetic storms. Hardened grid infrastructure, early warning systems, and operator training are key to making sure we don't repeat Quebec's mistake. Level 4. Not all storms come from the sun. Some are born right here, inside Earth's magnetic cage. This is the radiation belt storm. It's invisible, relentless, and uniquely ours. When a geomagnetic disturbance ripples through Earth's field, it doesn't stop at the surface. It charges up the Van Allen belts, two massive zones of trapped radiation encircling the planet. Normally, these belts are stable, predictable, but not today. Today, trapped protons and electrons go rogue. Radiation levels spike. Charged particles flood into low Earth orbit. Satellites that pass through get hit hard. Microchips take the brunt. Subtle glitches, timing errors, sudden failures. Solar panels degrade, not from age, but exposure. It's not dramatic. There's no explosion, but you'll notice when the forecast is off by 500 miles, when your GPS drops you in the wrong city, when a key satellite silently dies, and no one knows why until it's too late. This is death by precision loss. No blood, no flash, just silence. Using polar orbit avoidance and scheduling satellite maneuvers during quiet solar periods reduces exposure to these radiation surges. Engineers design critical spacecraft with radiation-tolerant components so that storms in space don't become disasters on Earth. Level 5. Imagine being inside a nuclear reactor. Now remove the walls. Take away the concrete, the lead, the shielding. Leave only your skin and a spacesuit. That's what astronauts face in a solar particle event. It's not light, it's not heat. It's a blizzard of protons moving at nearly the speed of light, tearing through tissue and electronics like bullets made of energy. If you're on Earth, the atmosphere and magnetic field absorb most of it. You're safe. But if you're on the Moon, or even in high Earth orbit, you feel everything. It hits bones, blood, DNA. Acute radiation sickness doesn't need days, it needs hours. Nausea, headaches, vomiting, internal bleeding, organ damage, death. In October 2003, the Halloween solar storms hurled proton showers so intense they would have sterilized an unshielded Mars crew. Those particles screamed past the red planet faster than warnings could catch them. This is why NASA watches sunspots like a stalker. It's not paranoia, it's survival. Because from the moment the flare erupts, you have minutes to act, no second chances. That's why today's spacecraft are more than machines. They're bunkers. Deep space missions now include radiation shelters lined with water or polyethylene, materials that absorb proton radiation far better than metal. Autonomous alert systems constantly monitor space weather and give astronauts just enough time to retreat into shielded safe zones, whether aboard the ISS or inside future lunar habitats. In deep space, safety isn't about bravery, it's about knowing when to hide. Level 6. It doesn't just break tech, it breaks trust. 1 second everything works, the next dash, nothing does. The stock market halts, automated trading systems freeze without timestamps. Weather satellites go offline, storm tracking misfires, flood alerts delay. GPS systems scramble shipping lanes, vessels drift into danger. Air traffic control switches to manual, radio-only backups. Military radars glitch, defense systems misread incoming data, and all of it because of the sun. Not a war, not a hack, a solar tantrum, an X-class flare, the strongest solar category. Followed by a full halo CME, where a cloud of plasma engulfs Earth head-on. This was the reality in 2003. Satellites reported radiation off the charts. Astronauts were ordered to shelter inside hardened modules. Airlines rerouted flights over polar routes. And we got lucky, because the storm missed Earth's direct line of fire by a few degrees. In 2022, we got another taste. A weaker version, but still enough to knock out communications across multiple regions for hours. If an event like this strikes again, head-on, during solar maximum, it wouldn't just be noticeable, it would be paralyzing. Imagine waking up, opening your map app, and the satellites are gone. No GPS, no weather radar, no data syncing, just silence in orbit. Redundant satellite networks, early CME detection, and automated spacecraft shutoff systems are how we dodge total blackout. Modern satellites now go into safe mode automatically, shutting down non-essential systems to ride out the storm. Ground control builds resilience in every launch. Because when the sun screams, there's no time to reboot, only time to brace. Level 7. There's no fire, no thunder, no explosions in the sky. Just invisible lightning from 150 million kilometers away, and it doesn't care where you are, not even if you're grounded. Planes stall on tarmacs, unable to communicate. Oil pipelines overheat, their control electronics frying from buried surges. Train signals misfire, a green light becomes red. Banking networks desynchronize, cutting millions off from their accounts. And in high-latitude countries like Canada, Sweden, or Russia, it gets worse. These regions sit under Earth's auroral ovals, where solar particles pierce the magnetic shield more easily. Ground-induced currents, GICS, ripple into power grids. They ride underground cables, melt transformers, detonate substations. Not from age, not from wear, from magnetic attack. It's not war, but it feels like sabotage. In 1921, the New York railway storm fried telegraph systems. Metal sparked, switchboards caught fire, and that was before we had microchips. Today, the consequences would cascade. A blown transformer isn't a blown fuse. It's years of replacement time. And in winter, that delay could mean blackouts in entire cities for days. Utilities in high-risk regions now deploy storm mode protocols, designed to decouple long-distance power lines, reroute current, and isolate high-value transformers from magnetic overload. Real-time monitoring combined with crisis simulations ensures operators know exactly when and how to respond. Because in a geomagnetic storm, timing is everything. Level 8. The sun pulses. Not once, not twice, but daily. Flares, CMEs, plasma bursts, stacking, layering, feeding each other. Welcome to solar maximum, a peak that comes roughly every 11 years and stays. This isn't a single event, it's a season of chaos. The sun becomes a boiling spotlight. Solar activity increases tenfold. Sunspots bloom like bruises. Storms overlap, crowding space with radiation. Satellites don't drift anymore, they dodge. Rocket launches are postponed. Signal timing wobbles. Orbit correction becomes daily routine. In 2022, SpaceX lost 40 Starlink satellites in a single solar storm, launched into what should have been a stable orbit. But solar activity heated the upper atmosphere, causing drag. They never made it to altitude. They burned up like fireflies. On Earth, the effects multiply. Auroras blaze across Florida, over Spain, through China. Beautiful, but ominous. Grid operators scramble. Power surges ripple like waves through national infrastructure. And the economy watches the sun now. Because markets tied to timing, signals, and precision don't react well to space weather. Solar maximum doesn't knock once and leave. It lingers, weeks, months, years. And every day it stays, it raises the chance that one storm, just one, could end everything. Preparing for solar maximum means integrating space weather awareness into everything, shielding satellite cores, decentralizing grids, and running blackout response drills as seriously as earthquake simulations. Because when the sun is angry, we don't get to opt out. Level 9. The sky is expanding, not figuratively, literally. Solar storms pour energy into the thermosphere, the thin skin of Earth's upper atmosphere. It heats like a balloon over fire, swells. But then the storm ends, and it cools. Fast, too fast. The thermosphere contracts, dragging down everything inside it. We call it a thermospheric collapse. Satellites once orbiting in harmony suddenly face drag they weren't built for. Their trajectories skew, their lifespan drops, their control systems overwork, thousands of small corrections, thousands of near misses, and it only takes one mistake. One satellite crash can send shards of debris in all directions, and that debris becomes shrapnel, each piece a bullet, each bullet a satellite killer. This is how we get Kessler syndrome, a runaway chain reaction of satellite collisions, where Earth's orbit becomes so crowded with debris that space travel stalls for generations. You look up, and for the first time in history, satellites rain back down, not burned up on re-entry, but pushed, dragged from the sky by the Earth's own breath. Space agencies now monitor atmospheric density daily, using models to predict drag and adjust orbits preemptively. Collision avoidance systems and debris mitigation protocols are baked into every satellite launch. because the higher we fly, the harder the fall. And sometimes it's the sky itself that lets go. Level 10. From Earth's magnetic poles, it rises. A glowing fountain of plasma. Normally, it's beautiful. A background process, a cosmic chimney that vents charged particles away from the planet. But under the pressure of a strong geomagnetic storm, it becomes something else. A plasma fountain eruption, invisible to the naked eye, but devastating to electronics. It rises vertically, then collapses back, showering the ionosphere with radiation. High-frequency radio goes silent, navigation errors grow. Low Earth orbit is littered with brief, violent bursts of energy. Airliners feel it. Autopilots glitch, instruments spike, and no one sees it coming. Because there's no visible wave, no warning flash, only silence and static. Ionospheric observatories and polar monitoring systems can detect and model these eruptions in real time, allowing airspace regulators and satellite fleets to make rapid safety adjustments. Level 11. Imagine Earth's magnetic shield. The magnetopores compressed to the edge of the atmosphere. That boundary, normally tens of thousands of kilometers thick, becomes razor thin. Then it tears. For a brief moment, the sun doesn't knock. It touches us. Charged plasma punches through directly into the upper stratosphere. Ozone cracks. Aircraft radiation spikes. Ground-based sensors pick up EM signatures usually reserved for deep space. Satellites built for vacuum are suddenly exposed to direct solar wind. Some fry in microseconds, others tumble, no longer controllable. This isn't theoretical. Simulations suggest that a fast, dense CME traveling over 3,000 kilometers per second could do this. And we're getting better at spotting those, but not stopping them. The magnetopause is the Earth's first defense, and sometimes it folds. Advancing magnetosphere modeling and placing redundancy in critical satellite systems can minimize total data loss during rare but intense compression events. Level 12. It starts as a flicker, but this is no ordinary flare. It is a super flare, something seen on other stars, rare but real. A sudden release of energy 10,000 times stronger than any recorded flare from our sun. For years, we thought the sun was too stable, too quiet. But then we saw it happen elsewhere, on stars like ours, and we realized it's possible. If it did, it wouldn't just disrupt satellites, it would erase them. Power plants would vaporize, transformer cores would melt from within, shielding wouldn't hold because it was never designed for this. The flare could strip away satellites' shielding in seconds, ionize the entire upper atmosphere, turn radio and radar into noise. It's not science fiction, it's a probability curve, one we don't fully understand, one we hope stays flat. Though we can't prevent superflares, future spacecraft are being designed to operate autonomously with auto-shutdown protocols and backup communication networks stored underground. Level 13. Now zoom out, past the sun, past the planets, into the galactic current sheet, a ripple of magnetized plasma that flows through the Milky Way. We drift through it every few million years. And when we do, the entire solar system feels it. Charged particles build, magnetic alignment shifts. Earth's magnetosphere isn't destroyed. It's flooded. Some scientists believe these waves are responsible for mass extinctions. Others think they're benign. But if one hit during a solar maximum, it would be like pouring gasoline on a forest already burning. Plasma storms amplified, geomagnetic chaos sustained, not for hours, for years. Communications may never stabilize, satellites may become obsolete, and Earth's atmosphere might begin to change, subtly, permanently. Deep space monitoring missions beyond Earth orbit could detect and map the edges of galactic plasma waves, offering humanity decades of preparation, if not protection. Level 14. This is the end of the scale. Not a storm, a scream. The sun, in its final moments, collapses inward. Not a peaceful fade. A violent transition, one last ejection of magnetic chaos. An interstellar plasma pulse carried on the back of a dying star. The heliosphere vanishes, solar wind ceases, the magnetosphere shrinks to nothing, and Earth, stripped, exposed, stands bare before the vacuum. Satellites don't fall. They melt. Magnetism, as we know it, ceases to matter. Only heat, only radiation. This hasn't happened. It may not for billions of years, but it could. And if it does, there's no mitigation, No forecast, no grid to repair. Just light, and then none. While this event is purely speculative and far future, studying the magnetic life cycles of other stars helps us understand how our solar system might end and how long we have to adapt. What if the next big blackout doesn't come from Earth, but from the Sun? Share this with someone who needs to know. Like, subscribe, and join us as we uncover the storms hiding in space.